This is actually a photo of one DAG facility. It does happen to be ours, but it would be very similar to a whole bunch of other DAG facilities. So what you see here is our facility is located in Alberta, in Canada, and it is located in an industrial park in a community of about 7,000 people. So first and foremost, it usually is not going to be located near a really large urban center, and it will usually be located in a place where you can actually access storage, which is really important. However, those places can be close by to communities as well. So just from afar, you can see that it integrates quite nicely with the natural environment. It is not that jarring, and it also does not look that different to a whole bunch of other industrial facilities that you see nearby. So very fun fact, we have actually a brewery right here. So you see another CO2 tank right there, which is the exact same size as the CO2 tank at our facility. So again, nothing that intrusive and actually quite able to mix in with the rest of the infrastructure. What you don't see on the right-hand side is also there is a facility that converts locomotives from diesel locomotives to hydrogen-powered locomotives. So again, when we think about decarbonization and we think about all of the different pathways, direct air capture can actually slot in very nicely to some other existing pathways. And it is not necessarily something that is jarring or very, very large when we're thinking about that facility. Now, this one right here is only for about 3,000 tons a year, so it is relatively small compared to the commercial scale that we want to reach. So it is also important to remember that when we think about very large scale, you want to have a lot bigger fields that look a little bit like this. And you will always have a bit of a processing facility, which is what you have here in the white room. You will always have a CO2 storage tank because you ultimately need to store and buffer. And then you're going to have a storage well, which I'm going to show you in a minute. But that is the least intrusive one in terms of actual infrastructure. It is actually about my size. So we're going to see some photos of it, but it tells you a lot in terms of what a DAC facility looks like. And the reason why I wanted to show you from this perspective is I think all of us have seen pictures of islands. We all know what that gamut looks like. And they are very fast and incredible facilities. But what I also want to show you is what it would look like when it's actually integrated in an industrial park. So with that in mind, let's try to actually zoom in. So this is a little bit of a close-up. What I want to talk about here is the fact that at this exact facility we actually have a multitude of direct air capture technologies at site. And the really interesting part that I want to emphasize here is that they all look very, very different. And so when we think about direct air capture, it's really important to understand that there's multiple technologies. There's actually over 150 technology vendors that have developed and are looking to scale direct air capture systems. And they are all taking very different approaches. And when you try to categorize these approaches, there's two main arms. There are liquid sorbents and solid sorbents. And at this facility, we actually have both of those, which is quite interesting. But they also all have one thing in common, which is that they all have very large fans. Even with the large fans, however, you will start to see that they are all placed differently depending on some of the different technologies. So Tom and his engineering team have their fans on top, and you can see they're very distinctive on the Mission Zero unit. The guys at Flare have them actually horizontally rather than vertical, so you can't even see them in the photo. There is an air hide unit here, which is again on the side, a little bit hidden. There's a Spy Renew unit here, which similar to Mission Zero has it at the very top. And then you see Carbon Capture Inc. over here, which is similar to the Climeworks layout. Every single one of these modules actually has a fan. So everyone has a fan because everyone is moving a whole bunch of air. Now this is where it gets really interesting. So everyone moves lots of air. What they move it through ends up being distinctive. Okay, so we got to the part where we're pushing lots of air right now in the base. And this air, which is poured by all of the fans, goes in contact with a sorbent. So every single one of these distinct technologies does have a sorbent. And this is where I was trying to say sorbent can be at two different kinds. It can be solid or it can be liquid. When it comes to liquid sorbent, we have two technologies at our site that have liquid sorbents. So you see Mission Zero as well as Flare. And when it goes to solid sorbents, we have multiple technologies that have solid sorbents. And what is interesting to note as well is solid sorbents can also be of multiple types. You hear a lot about amines or amines, depending on which side of the ocean you live on. But there's also other ones that get used within the process. So this sorbent, the best way to think about sorbent is basically a sponge. As you put large quantities of air through the sorbent, what you will have is saturation of that sorbent with CO2. So the best way to think about it is that it's a sponge. You put a large mass of air through it, which has a 435 ppm of CO2 as of May, I think. It's probably a little bit higher now than it was in May, unfortunately. And that sorbent basically becomes saturated with CO2. So it's the same as you would have a sponge which gets saturated with soap. And then you want to apply a variety of different techniques realistically to separate the CO2 from that sponge. And this is again where you have a lot of variability for all of the different technologies. So some of them use a temperature swing. So you end up having very, very high temperatures to be able to remove the CO2 from the sorbent. And that's where you will probably hear a lot of folks saying that DAC is very energy intensive. So when you start to think, okay, where is the energy intensity coming from? It's from the fact that you're actually using a really high temperature to actually remove the CO2 from your sorbent. So a lot of the equipment that we have that uses that process will go up to 900 degrees Celsius. As you can imagine, that is extremely energy intensive. Another type would be a pressure swing. So at that point, you do have a whole bunch of pressure vacuums and systems that basically try to suck out the CO2 from the sorbent. That is usually less pressure, less energy intensive, but still obviously fairly energy intensive. And then you do have a variety of technologies which use electricity or electrodialysis to separate the CO2 from the sorbent. And those ones are obviously a little bit more OPEX intensive because they do use electricity, and renewable energy is sadly expensive because there is a race for green electrons everywhere. However, they are more promising from the perspective of not using such high electricity for something like temperature swing, as I was mentioning before. So what I've told you so far is that there's multiple ways of having of using sorbent and multiple sorbents, and there's also multiple ways to remove the CO2 from the sorbent. And so what you end up having is a very interesting combination of every single technology basically saying, okay, we need a lot of air, but we're going to have a very different layout. The fans are going to be on top or on the side or in a different configuration. We're going to use a sorbent, and we have multiple options in terms of what the sorbent can be. And then we also have multiple options in terms of how we actually remove the CO2 from that sorbent. So you can already start to see that there's endless combinations to some degree of how you actually do direct air capture. And the end output of all of these different units, which is really important to know because this is the point at which we become uniform again, is actually CO2 gas. And this is the point where I think a lot of people misunderstand what exactly you do with direct air capture, but the output of a DAC unit is CO2 gas. And what's really important to know is that depending on the configurations that everyone chooses, you do end up with slightly different configurations of that CO2 gas. What do I mean by configuration? The most important one is purity. So when you have a DAC machine work, your output is CO2 gas, and we really need it to be as pure as possible. So at least 98% pure CO2. Now, you can obviously still work with less pure CO2, however, you end up with very high OPEX to try to clean that flow of impurities before you actually can store it. And why is that important? So let's actually go into the storage part because it's really interesting as well. So what you see here is basically a whole variety of units giving the CO2 gas that I told you about to that big white building. In that big white building, we basically process that CO2 gas. And given that this facility has multiple technologies that all produce slightly different CO2 flows and CO2 concentrations, we have a pretty intensive system to actually clean it of any impurities. So what we do is we make sure there is no nitrogen left, we make sure there is no other components left there that would have also been sucked out of the direct air, which is our feedstock. And then we create a supercritical pure CO2. At this location, we actually liquefy it to prepare it for storage. And the storage is basically what drives a lot of these requirements, because to safely store CO2 underground, you need to ensure that you're able to keep it there for over 1,000 years. And you also want to ensure that your well for which you are storing it is actually able to maintain its integrity for a really, really long time for it to be able to inject lots of volume. And CO2 is not the friendliest of substances. So if you do not clean it of impurities, what you will have is your well will corrode. And at that point in time, wells are pretty expensive to drill but also to maintain. And if you do not have clean CO2 and you have a well that corrodes, it means you can have leakage. It also means that you basically cannot continue injection. So you are in this situation where you cannot inject your CO2 and produce credits. And you are realistically left in a little bit of a pickle, either to go do another well or to spend a lot of money to fix your existing well. So that's why CO2 purity is really, really important when we think about direct capture. If you were to use it just for another use case, you would still have to clean it for that use case. But because of the permanent storage aspect, you really have to do a good job of that to be able to ensure that your well is actually integral and maintained that way. So now that we talked a little bit about storage, I do want to show you just a few close-ups. Just to show you how different direct air capture systems can be. Again, we have a close-up of Mission Zero, so Tom's here to validate that the best spot at our facility is actually the patio at Mission Zero. This is where you can take the best photos, especially at sunset. So we're very grateful that they made a patio on their unit to receive people. But again, now that we've talked a little bit about how DAC works, I think it's nice to relook at the technology, right? So the air basically gets sucked in from up top through those big fans. Then it goes into contactors. So these two big units are basically where ambient air meets their sorbent, and their sorbent specifically is liquid. And after which it gets processed, and what we get as the facility that is basically CO2 gas pipelines. So those pipelines get the CO2 gas, it gets connected. Check. Okay, there we go. Sorry about that. So we're able to measure it as it leaves the Mission Zero unit. And we are able to know exactly the purity, exactly the composition, the flow, which is also giving us the volume. And we are also able to know how much electricity was used by this particular unit. Because what's really interesting at the very end is to know how much you produced, how pure it was, and how much electricity you used to be able to do this. So this shows you, again, a little bit about the very, very large variability in what DAC looks like right now, which I think is really important to acknowledge. Because I think a lot of times we think about DAC just as a really big Climeworks stands, and that's not necessarily it. There's a lot of different ways to do direct air capture, but the elements stay the same. You're always going to have a really big fan, you're always going to have a sponge, and you're always going to have one of the methods to remove the CO2 from that sorbent. And your output will always be CO2 gas. Even if you look at facilities that do ESAP or facilities that combine it for net zero cement, your output from a GAC unit is always going to be CO2 gas, and then you might be able to do something with that CO2 gas as an output, or like we do, inject it underground to be able to then produce a carbon credit. Now looking at Flare, which is another unit, as you can see, their fan is basically not on the top, it's actually vertical. It's on the other side of this building here. And they are producing everything in a much smaller container. Now, what I would love to do is play a little game with you now. If you were to guess, what do you think is the capacity of this unit, knowing that you looked at, actually we should play with Mission Zero as well. What would you say is the capacity of this unit in terms of tons per year removed? And the entire facility that I showed you, everything altogether is 3,000 tons per year. So with that in mind, do you have any guesses how much this one produces per year?
500.
Okay, so this one is 250 tons per year. And let's play the same game with Flare. How big do you think this one is?
500.
This one's 20. So I think the other really interesting point that I want to make here is that because there is no standard design, there is also no linear scale between how big a unit is and how much it actually produces yet. And that's a really important point to actually be transparent about right now for that. Because sometimes you see really, really big units and systems and you might be thinking, oh my goodness, this is amazing, how great. But that doesn't necessarily mean that that technology is ready for prime time. So this is a great unit. Now, if we were to get a little bit deeper, both of these are liquid sorbent units, for example. One of them tells me that they're going to operate in the winter, and so I'm very interested to see how exactly they're going to do that. Because another key point to understand here is when you have a liquid sorbent, you are more likely to have the impact of cold weather and therefore freezing. So a lot of the liquid sorbent is not yet ready for winterization. So when we think right now about large-scale deployment in very cold climates, it is a lot more likely to have solid sorbents be deployed rather than liquid sorbents due to the fact that we have very, very cold winters that we have to withstand. So it's an interesting point. Team at Flare is fantastic, so absolutely nothing against it. What I'm trying just to show you is the variability in design, the variability in size, and also output at this specific point in time in terms of where the industry is. Just because it's variable, it doesn't mean that it's not producing. It doesn't mean that we shouldn't continue deploying. But I think it's really important just to understand the exact point in time we are in to better understand the industry and also to better understand where we go from here. And then last but not least, I wanted to also show you a solid-based. So this is the carbon capture ink unit, which looks a lot more like what a traditional DAC that you might think of looks like. It actually is very similar to the little infographic that we have on the wall right behind that gentleman there. So you see the fans and the configuration, and you also see the CO2 storage tank that then goes underground. But this unit is basically using a solid sorbent with lots of fans, and it is also very similarly producing CO2 gas. Now, let's play this game again. What do we think is the capacity of this one?
You know what I'm going to say.
500 now? This one is 2,000. But I think this is why I wanted to play this game, because I think the point gets really interesting. So what you see here, for example, is they have 4 distinct modules. So each 12 is basically a module for them, and each module is 500 tons per year. Now, they also have some challenges in terms of interoperations. So solid sorbents are not completely impervious to winter operations and the temperature. However, they believe that they can run as cold as -10. And that's where we were going to try to work with them to push the boundary in terms of how they can do it. A lot of it for units like this, which is again very similar to the type of units which are very popular in terms of images and popular knowledge, is actually that the system works. However, the mechanical doors that open and close to allow air in freeze during the winter. So that's a very solvable problem, which is the good news. However, it's interesting to know that there's a lot of criticism sometimes about DAC, but when you actually get to the brass tacks of what problems we need to solve, it's mechanical doors opening and closing in cold climates. So, you know what, that's not a very difficult problem, and I have a lot of faith that we figured out how to go to space and lots of other things. We're going to figure this part out. And I think that just shows you, again, a little bit about the type of information and misinformation that can sometimes cloud our judgment when we think about or speak about a new type of energy. All right, and what happens to all of the CO2 gas that we process? I promised you guys that I will show you the last part of it, because when we talk about direct air capture, I think a lot of times we focus on the capture part. And so what we discussed is you capture it, after you capture it, you process it, and once you process it, you need to store it. And this is where it gets really interesting. From the point of view of, there's lots of countries that have a lot of experience in storing gas. Specifically, Canada, for example, has a lot of experience storing sour gas, which is a byproduct of a lot of oil and gas operations. So this is actually a very vanilla facility when it comes to Canada and what Canadian engineers can do. But it is very much a hot topic, right? So I know, for example, there was a lot of opposition in the UK to ever considering CO2 storage on shore. So the UK only does it offshore in their wells that are in the sea. Germany had banned CO2 storage up until last week, when they basically said that they will reopen consideration of CO2 storage. However, most of it will looks like most of it will be under the North Sea, so also offshore, with pipelines taking the CO2 gas to those wells. So Canada is one of the only places where we are really talking about CO2 storage onshore, which means that, this is close by to a village, close by to a community, and a lot of the social acceptability and community engagement you need to do to actually store CO2 is really interesting. Given Canada's background in energy and the fact that folks have seen operations like these before, it has been a lot faster to do so, which allowed us to be able to be quite quick with this project. But to give you guys a little bit of a view of what this site is actually focused on, you see right here there's a little wellhead. It's red. It's really 5'3". I'm 5'3". I stood next to it. I'm telling you, it's exactly my size. And that is actually where you inject the CO2. Everything else is basically infrastructure, so you can do the injection. The real wellhead where you put the CO2 underground is that little red wellhead there. Now, what you don't see, obviously, is everything that's in the ground. So underneath that wellhead, you have 2 kilometers of pipe, which is pretty expensive. It does have to be steel reinforced for parts of it, because otherwise the CO2 will corrode it. And especially if you have interactions between the pipe and the saline aquifer you're injecting, you might have all kinds of interactions with the metal. So you need to make sure that it is a very specific finish to be able to use it for a very long time. The rest of the equipment is basically pressurizing equipment and packer equipment, which basically means that it creates the right pressure to inject that CO2 in the well and make sure that it goes all the way down to 2 kilometers underground. And the other part of this is you might see a fair few wires over here. This is actually the famous MRV equipment. So we talk a lot about MRV, and I think it sounds very good and very digital when we really talk about it from the registry perspective, what MRV really looks like for CO2 storage is a whole bunch of fiber cables that go down the well to actually monitor that the CO2 goes underground and stays underground. And so, again, the hardware of a lot of this stuff is not the most glamorous. And I think a lot of time we talk about very pretty slides and very pretty infographics. So I actually wanted to show you what it looks like in reality, which hopefully is interesting. The other parts of this, which are obviously pretty simple, are basically just a CO2 storage tank. So for a very large commercial operation, you're going to be able to just basically dock the CO2 transport truck or a pipeline and connect it automatically to the wellhead. This is a really, really new facility. So this photo is actually from last week. And as you guys can tell, some of the parts are still being finalized and in construction. So what we are doing right now is every single transport truck from our facility goes and gets connected to the wellhead to be able to inject. And once it's underground, it will stay there for 1,000 years. We're going to measure it and make sure that it stays there and there's no leakage in any way. But that would be the end of the life cycle for a DAC project. So I will stop there and hopefully have any fun questions. Hopefully even some of you who knows a lot about DAC still have questions. You talked about pushback against storage facilities. I'm curious why that is. I didn't realize that there were any public safety issues in relation to storage facilities. And then also a follow-up question with storing CO2 underwater. Does that not present any risks in terms of leakage into the ocean system? Thanks for the question. So, in terms of public acceptability, I think there isn't really a good reason to have pushback. However, there is a fair bit of misunderstanding about what CO2 storage is. So, what a lot of folks don't necessarily understand is that this is really, really deep. So, a lot of questions arise around the fact that it could interact with the aquifers used for drinking water or for agricultural use water or anything like that. Those aquifers are usually around 200 to 400 meters deep in the ground, whereas we inject at 2 kilometers deep. So we actually have absolutely no interaction with the aquifer. So that's one thing. The other one that emerges sometimes is seismicity. So will our drilling cause any impact on seismicity and will it cause earthquakes, basically, as you inject? There's a lot of data on this, specifically in Canada, again, because we have so many wellheads in Canada, which basically prove this. However, given the fact that this is a new type of storage, people do come out with the same question again and again. On your point about injecting underwater, so I did mention a saline aquifer, however, we are not injecting underwater. So from our perspective, it's all onshore. If your question is related to those offshore storage wells, which is basically drilling in the ocean, realistically, a lot of those are even deeper than what we have here. So at that point in time, there's exactly the same protocols in terms of not having any leakage and not having the engineering done in such a way that leakage is not possible. So a lot of them will basically have an additional well where if there is leakage, it goes into that well and can get contained, or other systems like that. That would be more so the area of expertise of folks from the UK, for example, as well as Norway. So Norway has a really interesting project. It's called Northern Lights. Their CO2 storage well is offshore and it actually gets transported by barge. So we transport ours by truck for this facility. In Norway it gets transported via boat. But they would be the experts in terms of doing that. So far in Canada we have only done CO2 storage inland. And so I think they are probably the best place to talk about those regulations. And I know they've been doing it safely and that facility has been operational for a couple months now. Thank you so much for the presentation. It was really good and very clarified. I was wondering, what is the lifetime of the plant? Yeah, that's a a great question. So in terms of the lifetime, I think the best part is to take it by each stage. And since storage is up here, the lifetime of the storage well is basically until the reservoir is full. And based on all of the geological modeling that we have done, wells like this can actually take millions of tons. So we have a big problem in terms of developing enough capacity and scale to actually fill a well. So one well right now should be good for the facilities we have for 20 years at least. So I think the critical path or the factor stopping us right now is definitely not storage. Now, when we think about the actual direct air capture facility, the White Dome, which is all of the gas processing, is also going to be good for 20 plus years. So this is infrastructure that, as long as you maintain, has a really, really long lifespan. I think the real question is about the capture units, and this is realistically first-of-a-kind equipment. Our view is to run this for as long as humanly possible while incorporating upgrades and preventative maintenance and improving the units consistently. However, we are also, I think, realistic enough to know that that might have some challenges. So I think as we look across the board here, some of the designs, especially designs where they're on their third or fourth deployment, will most likely last a lot longer than some of the designs which are on their first deployment, just because there's data, there's learnings that were incorporated in the engineering. However, we will do our very best to work with the technology providers to have it last as long as possible. And I think it's good to run machinery even if maybe it doesn't operate as well as you want it to, because it will still give you invaluable learnings. But also, very transparently, this DAC facility is a commercial facility where we have sold the optics. So we also have an intrinsic interest to actually run it to be able to do good on our deliveries. What chemical reactions are taking place inside of those sorbents? Yeah, definitely. It's an interesting question, and I think a lot of engineers usually ask me that. There's a lot of it that unfortunately I can't divulge just because the different sorbents can be proprietary to some of the GAC technologies. But realistically, it's basically CO2 that is interacting with the sorbent. That probably tells you enough if you have a technical background. If you don't, it's basically molecules that interact with each other that bind the CO2 from the air specifically to the sorbent. And through that bind, they actually become saturated. So it does stick to the sorbent in some degree, after which you have to separate it. So that part too is quite energy intensive. It's the separation realistically that requires a fair bit of energy, and that's where a lot of that energy usage comes from. If you are to talk to any of the developers, they would probably tell you a little bit more about the technology, but I can't make one general statement just because it's so different. I think we have to wrap here, but thank you all for coming. I really appreciate it, and this is what a DAC facility looks like.